Thank you, Dimitri, for organizing it, and Madeline. Thank you, folks, for coming today. We'll do quick intros, and I'm going to try something somewhat controversial. I'm going to try to violate every law of live demos and do it. So what that means is I'll actually try to do live benchmarking on Redis and on Valkey, and we'll see who comes out ahead. Because one of my biggest pet peeves is blogs about performance benchmarks that are not reproducible. So we're going to try to go a step further. And if you want to follow along, you could. This is also recorded. You can follow along afterwards. That way you know it's not engineered or anything like that. So we'll get into this with that kickoff. Quick intros to ourselves. My name is Khawaja. I started my career building cameras for the Mars rovers. I'm super impatient. That's why I like benchmarking. Hardware is not very fast to work on. Like, it takes a while to see the results of fruits of your labor. So I moved into writing software, and I moved my image processing pipeline for NASA to AWS back in 2008 timeframe. Again, impatience works there. I joined Amazon. I was there for almost a decade. I ran the DynamoDB team, worked very closely with the Elasticache folks there as well. A lot of the folks from then are still on the team. It's exciting to see that as well. And today I'm a co-founder at a startup that also does caching. It's called Momento. I'm co-presenting today with Brian.
Hey, yeah, I'm Brian. I think my journey in all this stuff sort of started, I joined Twitter in 2014 and started working with one of my other co-founders, Yao, all the way back then. Obviously, things at Twitter eventually did change. So my team, which was responsible for doing a bunch of performance testing for the platform organization, we left and founded our own company. So we're basically doing the similar things to what we were doing at Twitter, but offering that sort of as a service and kind of taking our experience in benchmarking and caching and all that sort of stuff and observability and kind of spun that out into our own thing. So that's what I'm doing now.
Awesome. We work very closely together, the two companies. Sometimes it's hard to tell us apart, but we do different things. So just real quick about what Momento is, and I'll get into the Valkey benchmark. It's basically a two-tier cache, classic two-tier system. We've got a routing layer, we've got a storage layer, we've got a control plane. And the routing layer authenticates, and it sends data to the request to the storage node, sends it back. Very straightforward. Can get into debates about why that's better or worse, but that's not what we're here to talk about. Today we're here to talk about Valkey, and benchmarking Valkey, and about that, there's a tool that we're going to use to gain some insights on what parameters to tweak, and that is the tool that Brian works on.
Yeah, so at Twitter, we kind of had a need for some higher resolution observability sort of stuff. I was working on the cache team there, and so we cared about latencies that were sub-millisecond. Obviously, probably a lot of you are familiar with the demands of high-performance stuff since we're at a Valkey meetup. But yeah, I mean, there were definitely cases where minutely level metrics, or even if you had secondly level metrics, you might not be able to see everything that you want to be able to see. So I started working on this thing called Resolus, and sort of morphed over time, and now leverages eBPF very heavily, so we can instrument things in kernel space and really get a good idea of what's going on the system level. And this is really important for being able to understand what we see when we're benchmarking things. So there's a little dashboard view of some of the stuff where we ramp the load up on a Redis-like thing.
Called Valkey.
Called Valkey. I couldn't remember exactly what this one was from, but yes. We use this in our testing and to be able to understand the benchmark results that we're going to show you.
Oh. One of the things that Brian omitted in his introduction, so Brian and Yao, they work together. They also, I guess they were bored, but they went and rewrote a Memcache compatible cache in Rust, and it works really, really well too. But They're hardcore engineers. We have performance benchmarks on that too, but that's not what we're here to talk about. So the plan today, we're going to talk about SLOs and metrics, dive into our target, lay out the setup, and walk through our plan to hopefully get there. We're going to do a little bit of primer along the way, intertwined with this, to cover the concepts we will use to drive the system hotter and hotter. We're going to do some tuning. We'll do it live, inspired by Bill O'Reilly. And we'll learn a little bit about what parameters to tune, how do we know what parameters to tune, and you'll see incremental progress as we tune those parameters. So the goal today is, we don't want to use a metal box and show that it could do 1,000,000 RPS. That would be way too easy. We're going to limit ourselves to 8 vCPUs. So this is a Graviton 4 CAG 2XL. That's what's going to run the server. And it doesn't matter if you can run 1,000,000 RPS if it takes seconds to get the results. So we put latency SLOs. We're going to try to get we're going to stick under 500 micros, half a millisecond, on the P99, and try to get under a quarter of a millisecond for your average latency. I usually don't talk about averages, but the Valkey benchmark tool makes a really big emphasis on the average, so we should talk about averages. It's also important for knowing the number of connections and so forth. If you could be bound on throughput by connections too if your average latency is too high. But we'll talk about both of those, and that's our SLO. We're going to try to make it real-world-ish. Quick background on that. A lot of the benchmarks are very specifically tuned to the level of the packet size. Like I remember a blog where they were sizing the number of items in a pipeline to fit in a jumbo frame to demonstrate how you get to millions of RPS. None of that's going to happen here. We're going to try to be more real world, but the disclaimer is it's still a synthetic benchmark, right? So you want your benchmarks to emulate your specific scenarios, but remember that there's no better benchmark than production. We're going to try as hard as we can to make it a little more real-worldly. We're going to put client and server in the same availability zone, just to minimize that variability. And we're going to go a step further, and we're going to put them in the same cluster placement group. Now, cluster placement group is, for some reason, not as popular as I would have imagined it to be. But it essentially allows two EC2 hosts to be co-located closer to each other. They're not going to be in the same rack necessarily. They are just going to be closer to each other on the network. And that just means there's fewer hops, there's fewer variability on the network side, fewer packet losses, and so forth. And it just makes it easier for us to do more reproducible stuff. We're going to use the same node for Valkey and Redis. We're going to run one of them at a time, but it's the same node. So there isn't any sleight of hand kind of, Valkey is running on a faster node than Redis or anything like that. You're going to watch me turn off Valkey, turn on Redis, turn off Redis, turn on Valkey. We're going to do all of that. It is going to use Docker, but no fake pipelining. So when we say 1,000,000 QPS, it's 1,000,000 unary requests. And we're going to do hundreds of connections, stick with 1 kilobyte item sizes, and 3 million keys in the key space. Okay. Brian reads the manual, so he knows that when you go to EC2 and you see a spec on the EC2 pages for how much bandwidth is available, remember that's not the baseline bandwidth that's available to you, that's just the burst bandwidth. So technically, my benchmarks will violate the baseline bandwidth that's available to the host. But we're going to be running these benchmarks short enough so that the bandwidth is not going to get choked. But in his version of the test, he runs it with 128-byte objects so that you're staying under the baseline bandwidth. So that's one quick delta between the two things that we're going to do.
So Test. Yeah, so in my tests, I'm running closer to only about 1 gigabit per second effective, whereas Quadra's tests are running closer to 8 gigabit per second, which is a little bit over that 3.75 gigabit that you're promised with a C8G2XL, but it's fine.
You're not really promised them, but that's the baseline bandwidth. Sorry, I used to work at Amazon. There's PR training here. Words like guarantees are rarely used. But that's what makes engineering more exciting. Now, we all have learned that context switching is expensive. And I'm going to try a quick exercise. Like, you all already know this, but I want to make sure that you remember this when you leave. We're going to do this as a team. The first 10 letters of the alphabets, A through J. OK, so you don't have to count. J is the 10th letter. I'm going to count to 3, and I want everybody to just say A, B, C, D, E, F, G, H, I, J. OK? 1, 2, 3.
A, B, C, D, E, F, G, H, I, J.
That was pretty fast. Now say 1 through 10 really quickly as soon as I say 3. 1, 2, 3.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
All right, awesome. Now, I'm going to make it a little bit harder. I want you to say A, then 1, B, then 2, C, then 3. All right? Just a little bit more challenging. It should take you the sum of the time that it took you to say A through J and 1 through 10, right? All right, 1, 2, 3.
A1, B2.
You get the point. Luckily, we are. I'm not going to make a NUMA core analogy for human brains. All right, so now for the fun part. We're going to unbox some EC2 instances, and we're going to run the baseline performance and see what happens. And hopefully, it will give the results that we want, which is it should be able to get to 1 million QPS, but we'll see. Oh, are you out of batteries?
Yeah, I think that's what's going on.
I have engineers for my team here, so I just want to admit one of the other rules I'm going to violate is I'm going to do some stuff on the console. It's on my dev account. They took my prod access away, so it's fine. All right. So what we have here, there's a bunch of instances running, but the two to pay attention to is the CHG4XL instance. This particular instance is running in the same AZ as the other instances, and it has it's running in the same placement group as well. So it's running in a placement group called test.
Nice name.
And so is our benchmark instance, or the actual server instance. So what I'm going to do is, can't give this away. I'm going to reboot this machine so we can start fresh. All the configs will be lost. The only thing that will still be here is Valkey and Redis are installed on these boxes. But all of the network settings, all the pinning, all of that is going to disappear.
Make the text larger on that one, too.
I'm going to do everything as root, violating all the rules. All right. So let's start with Valkey. And let's just see what happens out of the box. So Valkey is up and running. All right. You can see, maybe you can see, but it says 172.31, 1493, 172.31, 1493. We're going to run some 50 million odd requests, and we're going to use 384 connections, key space of 3 million, 11 threads on the Valkey benchmark. And the interesting thing here, and I learned this the hard way, was we kept tuning the I/O threads, and Valkey wasn't showing performance delta, but RPC perf was, and then it hit me. You got to turn multi-threading on the client as well. So remember to do that, and the same parameters work. But we're not going to mess with the Valkey the benchmark, but let's go ahead and run this benchmark. And we are at a whopping, what would you say? That's like almost 250,000 RPS, 236K. The problem is it's going to take forever because I told it to do 50 million. But this is single-threaded, 233K roughly. The average latency is 1.6 millisecond.
And this is a pure write workload.
Pure write workload. So where it says -t set, that means it's a pure write workload. All right, this is going to take a while because we did 50 million. I'm kind of regretting that. But it actually means it'll take about 4 minutes. That's pretty bad. Okay. So you saw roughly. I'll read it to you for folks on the live stream, but 1.6 millisecond average, and about 250,000, 235K when we ran Valkey without any I/O threads. Let's make this a little more interesting. This time I'll only do 10 million, so it'll take 1 minute. All right. So 2 I/O threads, we went from 235 to 280. Let's just run the same thing with Redis real quick and see what Redis does out of the box. We'll jump straight to the good part and just do 2 threads on Redis as well. Very close. So we were at 283. Redis is at 276. Average and P99 latencies are still pretty terrible here on both sides. They're equally terrible in comparison. To what we will get to. I made a little scoreboard so we can keep score. All right, I'll take some notes. So all right. Average. For people who work on Valkey every day, do you ever love how autocorrect in Google always corrects Valkey to Valley?
You do need to add it to your dictionary. It's underlining spelling.
Yeah, but Google will still correct it to Valley. I don't know how to fix that. Okay, so 269K and 1.4 is the average. All right. So about the same. P99, let's just not worry about this. This is just way too bad. Let's see what happens if we add some more threads. I'm going to jump straight to 6 threads. Any predictions? Well done. So going from 1 to 2 didn't really make a difference, or as big of a difference, for this specific workload. But going to 6 got us to 868K. So with 6 threads,
Again, how many cores do you have on the machine?
the server, the Valkey, is running on an 8-core machine. The benchmark client is running on a 16-core machine.
And all the cores available to Docker.
That's right. All right, so just want to make sure I take accurate notes. Well, the latencies improved quite a lot too with this, with more threads. So average went down to 0.387. Oh, sorry. Should be 868K for V. And average was 0.387. And if we pause here, this is pretty fun to reflect on. Our throughput, more than tripled, and our latencies went down by a factor of 3. So that's pretty cool. Nice work, the Valkey team for I/O threads. I'm going to turn the same configuration on in Redis and just see what happens. All right, Redis improves a lot as well. You go to a whopping 618, 15, 14, 12, 11, 9, 8, 7, 6. OK, we'll let it finish. 596 KQPS. Not bad. I don't need to add a K here. All right, the average was 0.619.
Yep.
OK, and P99 is 1 millisecond. Let's just say 1.1 for Redis. And for Valkey, let's just scroll up real quick. Valkey was slower. 1.3.
It's a little unfair to compare latencies when the throughputs are so different there, though.
Yeah. 596 versus 868. Yeah, good point. All right. So now we've played with I/O threads. And this part so far is not quite rocket science from like the Valkey team and the Redis teams have made it really easy to just turn that configuration on, turn on IO threads, and boom, your throughput triples, latencies drop by a third. But let's actually get fancy. We're still pretty far away from getting to 1 million. So what are we going to do, Brian?
So, there's a lot of hiss on this microphone. So what we're going to do is we're going to look at why and what was actually going on the system level. So this is the Restless viewer looking at total CPU utilization on the server side in my test, which again was with 128 byte objects instead of 1 KB. But it gives us a good picture about how the CPUs are being used on this host. And we can see here with Valkey running that we have, we're at about 93% CPU utilization on the host, which is pretty good. One of our cores is running a little hot at like 97.7. So let's look a little bit further and see what is going on there. But quick, let's detour over to the client and make sure that the client is not where our bottleneck is. It's always good to double check these things. I was also using a much larger client in my test. I like to use a lot of resources when I do my benchmarking, but some of us are more conservative.
I practice frugality.
But in this case, the client is totally not the issue. We have so much CPU, we're only using like 30, 40% of the CPU on the box. Like, we have plenty. Next slide. Jumping back over to the server side, we can look at the amount of time spent in user space. And this is where things get kind of interesting because we can see that, you know, we're spending about 30% of our time in user space, but there's one core that's spending like 70% of its time in user space. So this kind of starts to expose what the threading model in Valkey looks like. We have one of those IO threads is actually like handling a bunch of the storage stuff. And it's spending basically all its time in user mode, and the rest are doing systems mode stuff like handling network requests and writing responses back out to socket buffers and stuff like that. But kind of sucks that like it's only using about 70% of a core. Like, this looks like our bottleneck so far. Next. Let's look at the amount of time spent handling soft IRQ stuff. So when packets are coming in, we have our kind of hardware interrupts on the NIC where things are sort of getting interrupted and context switching to handle those incoming packets. But there's also the soft IRQ side where the kernel is handling the packet processing as well. So if we look at the amount of time spent in soft IRQ, it's like 27%, something like that. And it's pretty even on all our cores. Now we saw that our one core was at about 97%. User space time on that core was about 70%, so this 27% gets us there. Like, we're kind of saturating when we combine our soft IRQ and our user space time on that core. It'd be really nice if we could get this out of the way and get that core up to 100% in user space, wouldn't it?
So, because we're masochists, we decided to not use pipelining, because the idea here was to be, to show real-world tests instead of just engineer the benchmark. But what that means is there's 1 million packets. Like, if you try to get to 1 million RPS, you're sending 1 million packets. It's a lot of packets for the kernel to handle. And
that's in each direction. That's 1 million for your requests and 1 million for your responses.
Great point. And these soft interrupts are going to happen as soon as the packet arrives, and they're going to interrupt whatever core was listening for it. And if your Valkey storage thread is running on it, well, tough. Pinning allows us to isolate the interrupts to just 2 cores. Brian, I, and Dan in the Elasticache team have been debating about whether 2 is enough or not.
Right. So, I mean, we saw 27% being used for soft IRQ time. It's an 8-core box, so that's sort of really annoying because you need like 2 1/4 cores to really handle it.
2.16.
Yeah. I mean, so maybe it needs 2, maybe it needs 3. I don't know. Like, it's hard to tell.
But roughly 2 is what you need.
Yeah, let's start there.
So yeah, let's try there and see if we can get this up to 1 million. So this is very simple. Like core pinning, it sounds really fancy, sounds really crazy, but it's just a few lines on Unix. So the first thing we're going to do, we're going to type IP link show to see what are the network interfaces we have. All right. This ENS34 is the actual network device that is on which the data is coming in. And what I want to do is I want to find out what are the interrupts. And you'll notice that for some reason, I don't know why, but for some reason, Amazon Linux defaults to having as many IRQs as there are cores on the box. So there's 8 cores on this box, so it defaults to having 8 IRQs. So when packets arrive, they will kind of interrupt whatever the hell's running on it, even if it's your Valkey application thread. So what we're going to do is we're going to say, you know what, let's get 2. And the command there is etool-l, name of the device. You say combine, and you say combine is just because the send and receive queues are the same. And you just say 2. So now there are only 2 queues on this device. Now what I'm going to do is, well, should we run this test again?
Yeah, let's run it again. We reduced it to 2, so I mean there should be some resources for that main storage thread to run free.
I'm going to do this with Valkey, actually, because it'll illustrate the point we're trying to make a little bit better, because it runs a little bit hotter. So I'm going to run a caveman tool, which is htop. So you can kind of see what Brian was talking about. So now, what you'll see is core 0 has almost none of the Redis or the Valkey stuff running. The Reds is mostly just kernel tasks. And but core 1 still has some Valkey tasks that get booted when packets are coming. So we got to do one other thing. But let's take a look. We're still at like 8:15. Let's take a look at what we can do here. So this command, --CPU set, I'm going to tell it to pin the Valkey process on cores 2, 3, 4, 5, 6, 7. That's 6 cores.
No, I'm going to let you do that, but you realize what the issue is, right?
5? 5 threads? Oh, Docker PS? Kill the old, no?
You haven't moved the network interrupts anywhere.
Oh, I got to pin the network interrupts. Thank you. Thank you. Usually I'm not holding a mic when I'm doing this.
Yeah, so the issue that we're talking about is the fact that the network interrupts, if you saw where they were coming in proc interrupts, it was core 0 and core 7, because IRQ balance was probably running, so be sure you disable IRQ balance as well. Otherwise, that's going to mess with us as we try and do really fun things. IRQ balance is going to try and be clever and mess up all our results. So we stopped that.
You want to explain what IRQ balance is real quick while I...
Yeah, so IRQ balance is a daemon that is running, and basically it tries to like look at the interrupt load and look at locality of the interrupt. So if you're on like an actual physical box with like 2 NUMA nodes, so you have 2 processors, or you have an AMD thing where it's all complicated, the network interface can be closer to some cores than it is to the others, and it gets really complicated. IRQ balance tries to do the right thing and tries to map the interrupts to the cores that are going to service it quicker, and it tries to look at all the devices with interrupts and try and spread things out so none of the cores are running too hot with interrupts, but we know better than IRQ balance does in this case.
In general, the operating system is trying to load balance and schedule things for you. We can just override that setting and say, please stay in your own lane for the IRQs, which is core 0 and core 1. So the way you do this is so we stopped IRQ balance. And then if you do the grep on the proc interrupts for ENS34, you see that there's only 95 and 96 are the interrupts, so the IRQ. So I'm just going to say, put a 1, which is pin this particular IRQ to core 1. And then I'm going to say,
no. You got to index by 0.
4.
So
you know what? I'm going to just do. No, this is fine. This is 2. So I'm doing SMP affinity, not affinity list. So this is 1, 0, 0.
No, it's still 0. It still starts at 0.
No, 2 is 1, 0.
Oh, you're
So
doing yes. Yes. Okay. Correct. There are 2 different ways to do this. This is using a CPU mask, which is a really masochistic way of doing this. I don't know why you're still doing this. But
it's basically 2 masks to 0, 0, 0, 0, 1, 0, which means that the second core, if you're starting from the end, is turned on. All the other cores are turned off.
Should be 96, but it'll be 96, right?
Thank you. This is called pair programming. All right, actually, I'll just show people how to do it the right way, if you don't want to be a masochist. If you say 0,
right, and put it out to the SMP affinity list instead. Yay, now we don't have to think in binary. Did you do that?
I did it again.
Yeah. Okay, now
All
it's
right.
good.
So the things to pay attention to is 95 is pinned to core 0, and 96 is pinned to core 1.
Thank you.
All right. Now we're going to run Docker with Valkey, and we're going to run Valkey on cores 2 through 7. This is 0 index, so it's the last 6 cores.
Your IO threads is 5 in that example. I was messing with him earlier and telling him to run this benchmark in some different ways, but there we go.
This is like code reviews on your benchmarks. I also recognize that I'm doing the Neanderthal version of benchmarking where I'm manually testing things. But here, now you can see a much more interesting pattern.
Hey, nice. That Core 6 is in like 100% of its time in user space. That's really good.
And the other thing to notice is the core 0 and 1, that's where the RIQs are pinned. They are saturated almost.
Yeah.
Let's see what the numbers look like. 1.02. So we beat the million by simply pinning to 2 IRQs. But I think we can do more. I'm going to try to just point out one other thing. Your benchmark node also needs to do IRQ pinning so that it's running efficiently as well.
Yeah, as long as you're using a smaller node, this is going to matter more because you're going to have 8 interrupts on the next size up as well. So reducing that to get that out of the way, the benchmark tool helps. The other thing to note is that the P29 latency came down like quite a bit with that change. So that's always nice.
Yeah, P99 latencies are at 0.55, and the average went down to 0.293. All right, on the benchmark node, for reasons that I don't want to get too far into, Valkey bench is a little less optimized for this than Valkey itself is. I have other things to say about Valkey bench too, but we're going to put three queues here and give it a little bit more horsepower as well. So the 3 queues are all right, so I've pinned Valkey bench network queuing to the first 3 cores in the system, and I'll run it one more time. You'll notice Valkey bench has 11 threads, and I need to do a CPU set on this as well. Let's pin the benchmark too. So CPU set 4 through 15. Give it 11 threads, 384 connections. Everything else is the same. Right. Got a little bit better. 1.05. Now you're really pushing these.
Yeah, those 2 threads handling all the soft IRQ are pretty hot at 99%.
Yeah. It's almost if they can use another 0.16 cores.
Yeah, maybe it does. Maybe 3 is a better number.
Yeah. We'll give that a shot, actually, before we end. There's another thing I'm going to do, as promised. Let's just see. This is a pretty, this configuration broke the 1 million QPS. Let's just run Redis with the exact same configuration and see what happens. Oh, we didn't meet our SLO. So the average was 0.343, and the P99 is 551 micros. So it's close. We can do a little bit more tuning later, but 550 micros for P99.
You could use a larger load generator.
That does help. He's not wrong. All right, same configuration. I just changed Valkey to Redis. I'm going to run the load test again. Not running as hot.
Ooh, bottlenecked on that storage thread, aren't we?
Yeah.
Can't make that core any faster, though.
Can't make that core any faster. And I don't think you're going to get much more out of it by adding more queues on,
Nah. You already
on this particular setup. Madeline, any theories as to why?
Oh yeah, we know why. We spent so lot of time on the main thread prefetching, so we try to execute commands like a batch. So we try to prefetch memory, so we're not waiting on a memory access stalls. So that's they're probably just stalling out, waiting for random VRAM access. And I think they know that too. So I think in the near future, the numbers will be close.
Nice. So here, the test is almost done. Same configuration, 718K. Because I want to make sure we leave enough time for Q's talk too, I just want to call out, like, we can, when we were messing around with this right before the presentation, going down to 5 I/O threads and 3 IRQs gets us to like 1.1 million RPS. So you can try that at home if you'd like. With a bigger load generator, because Brian has more funding than I do, he was able to get, what was the number you got on an 8XL?
I was getting like 1.24, 1.25 million QPS.
In all fairness, though, it was with a bigger load generator and smaller objects.
And smaller objects. Because I don't want to get bandwidth throttled.
That's right. So I think, did we cover all this?
No, this was sort of the, this is the sort of after view. So this is, again, looking with Restless at what was sort of going on. So we have total CPU utilization here. We can see that we have one core that's running kind of hot, but we've got all our soft IRQs out of the way, which we sort of saw with the HTOP stuff. And yeah, so now we see that the one core that is spending all its time in user mode executing actual storage stuff is at like 99.6%. So really good, like we're just kind of limited by the speed of that core at that point, or any other, if there are other optimizations. But yeah, this is great. All our soft IRQs are concentrated on, in my case, this is with 3 network queues, so it's all concentrated on the first 3, and they're at about 78%, so we know that we're not saturated there. And here's where we see kind of one of the cool things. This is TCP packet latency. This is measured with an eBPF probe that measures from the time that the kernel says, hey, there's data ready on this socket to the time the actual application reads it. So this is purely the delay for Valkey to read from that socket after it got a notification through something like ePOL. And we can see that when we reduce the number of network queues and we do all this IRQ avoidance stuff, our latencies go way down for TCP packet latency. So this is where a lot of the gain is coming in. Our P29 went from 400 micros to 300 micros, and we kind of eliminated about a millisecond off the P39 and 10 milliseconds off the P49. So this really makes a huge difference, and this is something that you're able to see with Restless because it's actually instrumenting and measuring that latency.
Syscalls.
Yeah, so one of the other things that Restless measures is the count of syscalls as well as syscall latencies. There's a bunch of stuff that you're able to get, again, using eBPF. So this is on the client side, and this is just sort of one of those things that makes me go, what? Because we're doing about 1 million QPS, but on the Valkey benchmark side, it's doing over 6 million syscalls per second. And if we go to the next slide, we can see that they're all in ePOL and friends. So one of the things, this is over 5 ePOL CTLs per request on average, which is not great. Like theoretically, you should just be able to do, ideally not many, you're just polling. If you go to the next slide. So the reason why this is because the benchmark tool is written using level-triggered equal notifications. And the whole benchmark is driven through these notifications. So level-triggered means that if the socket is writable, you'll keep getting notifications that the socket's writable. Not really super interesting when you're almost always writable, and generally you are. But the way the benchmark's written is that it needs these sort of notifications to kick off writing a request out. And then it re-registers as, hey, I want to know when this is readable. So it gets a response in, reads that, and keeps flipping it back and forth a bunch. So basically, just due to the way the benchmark tool is architected, you're getting these 5 system calls per request that you really just can't avoid. If the tool was written a little bit differently, like using edge-triggered notifications, you could probably avoid this. So that would be definitely an area to optimize the benchmarking tool.
And then maybe I can get the same results for the 2XL.
Oh, and then one other thing that I saw with system calls, and I didn't get a chance to look into this, is that there's some mutex contention on the client side when we're doing, so this is, our writes are happening first to warm up the Valkey instance, and then reads are happening at the end. But getting about 300,000 contended mutexes per second on the read workload is not great when you're doing about 1 million QPS. Or 1.2 million QPS. So
quick summary. When you're trying to run the system as hot as possible, 5 to 6 I/O threads work really well. Turn down your IRQs to 2 or 3, depending on whether you're running 5 threads or 6 threads. Turn off IRQ balance. Pin the IRQs to some cores. Pin the Valkey processes to the other cores. Luckily, Gravitons only have 1 NUMA core, so like you don't have to worry about NUMA locality or anything like that. And then do the same thing on the client side, and you'll get 1 million QPS. If you would like to not run your machines as hot, and you'd rather have 750K, you can just run Redis. If you struggle to follow along because we were trying to, do this live and all that, a lot of the instructions are on the blog that sparked all this. We'll share that in the Valkey Slack. If you're not already on the Valkey Slack, please join. There's lots of help, lots of community. People are just helping each other out. No question is too silly. Ask away. I have been asking a bunch, and there's really helpful folks who will just DM you and tell you what you're doing wrong, and that's been a really nice part of me, like the part that I've really enjoyed sitting on that Slack channel as well. And with that, I will pass it on to Q for the next talk, and then we'll take questions afterwards. Thank you.
Thanks.